things. So the bad news about this is that I was furiously getting this talk ready last night, went to sleep thinking that I had today to work on it while everyone else was talking, and now I don't. Sorry. Okay, so I'm not sure, this is also, the other downside is that it's not clear this is a good way to start the morning. But anyway, so I'm going to talk about partial differential equations. Although I guess the previous first speaker, Brenner, would have been more mathematical than I am, so consider yourself. So partial differential equations pervade the physical sciences, and the reason for this is that whenever you have a situation in which you need to enforce an equation at every point in space. Now people can hear me. Oh, you couldn't hear me before. Oh, I see. Well, okay, I didn't say anything, so I'll start again. So partial differential equations pervade the physical sciences, and the reason for that is that whenever you have a situation in which you have to enforce a physical law at every point in space, then you are given a set of partial differential equations, and these are come up everywhere in applications, and the sort of one that will come up at some point in today's talks are solutions of Maxwell's equations, which are of course critical for optics and imaging, among other things. So the Navier-Stokes equations, which are my favorite equations, they're here, copied from Wikipedia to show them to you, and they describe, of course, fluid flow, which will be important for Sella's talks on flood. They're important for the weather that we're now experiencing. They're important for turbulence, which I will discuss to some extent, and so on and so forth. Now, the reason that applied mathematics exists, so this is as a discipline, from the best that I can tell, is because on one hand, nominally, PDEs have an infinite number of degrees of freedom, but on the other hand, obviously that's not the case. If that were the case, you could never simulate them. If that were the case, you could never understand them. And there's sort of a body of work that's gone on for 150 years, which aims to basically figure out how to reduce the number of degrees of freedom in one way or another so that one can think clearly about what is happening. And I guess I have in the last couple of years, partly because I've been hanging out with the people at Google who have been here, and partly for other reasons, become fascinated with the opportunity for machine learning to essentially replace what we've been doing in these terrible applied math classes with all of these equations, and to replace them in a much more coherent way. And what I want to do today is give a talk which is going to be frenetic. It would be frenetic even if I had the rest of the day to prepare, but anyway, it's going to be frenetic, that basically just goes through 3 vignettes. So there are going to be 3 vignettes, which are going to just be 3 different examples of places in which it seems that there's an opportunity to use machine learning for PDEs. So the first vignette is on data-driven coarse grading. So this is to basically address the problem that one can never the primary driver of computing infrastructure, at least up until very recently, has been solving PDEs, and that's basically because you never can have enough grid points, and it costs a lot to do it. And so the only way really around that is to figure out effective equations which coarse grain degrees of freedom that you can't resolve. And I'm going to tell you about some work that Yohai, who's actually fortunately showed up there, so he can save me when I mess up, from Harvard, and also a group of people from Google, mainly Stefan Hoyer, who's a wonderful research scientist at Google, and what we've been trying to do to address this problem. So the second thing I'm going to talk about is some recent work by Ellen Klein, who's a graduate student in physics. Hopefully Ellen is here. She might not because, oh, she is here. Good. So you can save me when I need people to save me. So you can save me when I mess this up, which is about sort of using machine learning to try to invent a new imaging modality. It's not quite as grandiose as I just said, but you'll see when we get to it. And then at the end, I want to sort of tell you about a sort of crazy turbulence problem, but also just illustrates another way that machine learning can be used. And somebody's keeping time? Do you guys keep time? Okay, good. So I can stop. The beauty of this talk is I can stop at any moment, and the amount of content that will be left, well, it won't be very much. And also, you should interrupt, even though this is a big room, because I make no pretenses for being clear. So okay, so these are the people. So Yohai is here, Stefan, Ellen is in the back. Jacob Page is a postdoc from Cambridge who's been doing the last topic, if I get to it. Okay, so this is supposed to show you, if the slide works, they're supposed to show you 2 movies. So this is the weather. This is a simulation of the weather. And there are these, and which took, I actually forgot now, weeks on the largest supercomputers that exist. So on the right, there's a simulation of Rayleigh-Bernard convection, which seems to not be playing unless I click. Oh, and I didn't want to start it at the beginning. Sorry, see, this was the part of the slide I was going to work on. And you know, Rayleigh-Bernard convection is one of these boring things that only fluid mechanicians love. You heat from below, you cool at the top, and what you see are just tremendous structure. So the computational cost of these things is very large. It's, you know, if the mesh point is delta x and you're solving in 3 dimensions, then the computational cost is at least of order 1 over delta x to the 4th. And as I said before, this is why we have supercomputers. Now, the striking thing about these movies is that when you watch them, there are patterns. It's true that when you solve them for any given set of initial conditions, you have to just integrate pointwise in time, but there are patterns. And one might like, if I can get my pointer to work, to bootstrap of this. Okay, so the classical numerical analysis, the way that it works is the following. So this is an equation which is called Berger's equation, which will come up in a little while. What you're supposed to do is you're supposed to take the equation and then you're supposed to represent it on a mesh. The meshes might be equally spaced, and you might represent the velocity field at the ith mesh point by v sub I. And if you do that, then approximately the second derivative is given by this discrete formula. And if you then plug in these sorts of formulas into the original formula, you end up taking the PDE, which exists at every point in space, to a set of ODEs, which exist at only a finite set of points in space. And what you're supposed to do is solve that. So classical applied mathematics is all about the infinite number of ways in which you can do this, and how do you do it so that the computer doesn't screw up. That's basically, right, we have classes on this. Now the problem, of course, is that if you want to resolve what is happening, then delta x has to be very small. So just to give you a flavor for this is a photograph of the weather, and this is the simulated resolution in a state-of-the-art weather model. And what you'll see is that although the vortex looks like it's still represented over here, these are pretty big grid boxes. I mean, I don't know if you'll notice, this is Florida. And so these grid boxes are an appreciable fraction of the size of Florida. And that's, the reason for that is not because it's a good thing. It's not that everybody believes that nothing is happening inside of one of these little boxes. It's that there's just no way. You can't fit the damn thing on the computer otherwise. So, okay, so for realistic flows, it's basically impossible to solve this problem. And so over the last 70, 80 years since World War II, when this business really started, people have invented a variety of hacks. The most favorite hack is to change the equation and to invent what you might call an effective equation, in which what you do is you invent new terms in the equation that are supposed to account for the unresolved degrees of freedom because of some argument. And we, in applied mathematics classes, we can spend weeks on this, on just simple terms, like, oh, if you would only do this, and you can sort of pretend to rigorously justify it all you want. I don't know who I'm offending by saying what I'm saying right now, but I'm sorry. You can pretend to justify it all you want, but the truth of the matter is, when you push it to the interesting regime, it's almost always unjustifiable. They're basically curve-fitting exercises. They're exercises which have a strong scientific basis, but they're curve-fitting, and these sorts of things, hacks, go on throughout science. So for example, there's density functional theory in chemistry, which is a similar hack to basically put together solutions to the Schrodinger equations that basically make sense. And of course, these things are wildly successful, but on the other hand, they lack what one wants with the same. So what one wants, right, when one does a calculation is to have an opinion about whether or not the fact that it disagrees. Of course, the simulation should disagree with the experiment. But then the question is, but does it disagree because there's something else going on, or does it disagree because you couldn't do the calculation? And basically, because of this, it's pretty hopeless. Okay, so, and just to sort of amplify this more, if you open up COMSOL, like in terms of like hack models, for turbulent flow, look at all the models they have. It's sort of, this is like, each one of these is like, decades of work from people. But this just shows you that, depending on the situation, you're supposed to change the equations, even though everyone agrees that the Navier-Stokes equations are the right underlying equations. Okay, and I said that this conundrum has really driven scientific computing for a long time. Okay, so our idea is basically, in a nutshell, the following. So, as I said, PDEs aren't really, they are infinite dimensional, but the solutions at any finite set of parameters that you might be interested in is not infinite dimensional. And so, and it's sort of well been known in the mathematics community that the solutions for PDEs at a given set of parameter values define some sort of a low dimensional manifold. That is, the mathematicians prove theorems that say there exists a low-dimensional manifold on which the solutions live, and then they try to bound the dimension of the manifold. And for example, here's a famous paper from 1990 by Edris Titi, which is called On Approximate Inertial Manifolds for the Navier-Stokes Equations, in which he tries to explain what the dimension of the solution actually is at a particular Reynolds number. So, and then of course, so the thing about that is that if you could only parameterize that manifold, if you could describe it and you knew what it was, all of a sudden you've got a way to solve this problem in a without in a much more systematic way. And the problem that one of the problems that I think that we've had in the applied mathematics community over the decades is there's really been no way to parameterize this manifold. But of course, machine learning actually does offer at least a possibility for doing this. It gives actually many new different types of ways of approximating the manifold and using it for computation. And just to sort of start the meeting off in provocative and maybe wrong ways, what you would think is that machine learning should be good at getting rid of any ad hocery that you have. You should at least be able to use this to replace it with a different type of ad hocery. I guess that's fair. This is also ad hocery, but it's different than the other one, so you should be able to use it. So, okay, so in that spirit, that's what we're going to try to do. And so, I mean, just to sort of give you a thing, humans, when we see movies, well, maybe I'll just make a philosophical. So my friends at Google always, you ask my friends at Google, some of whom will speak later, so when should I use machine learning? So what they say is, well, if you can train a human to do something, then you should be able to train a computer to do something. Like that seems like a reasonable rule of thumb. And if you watch the weather, so suppose I gave you a movie of the weather, and I said, tell me what's going to happen next. You can imagine if you watched infinitely many movies of the weather, you might get pretty good at the rules, even if you didn't know anything, right, about the equations of motion. And so it should be possible, if we could only figure out how to teach the computer to do that, and then to use that knowledge to speed up simulations and to make them, maybe there are rules for the way these hurricanes move that you could figure out just from watching lots of hurricanes. Okay, so that was a long introduction. So let me now get into something more concrete. And I guess I want to emphasize that the broad idea that I just said is pretty general. I'm about to show you a specific implementation of it that we came up with, but there probably are better ways of doing this. This is just what we've been doing. So, okay, suppose I told you that these are 4 solutions to a PDE. And then, so what you would normally do is you would choose the grid points. So we choose grid points. And then you get rid of the line. And now what you're given is you're only given the solution on these coarse grids. So, so now in order to advance the PDE, I haven't told you what it is yet, but in order to advance the PDE, what you need is you need to know the spatial derivatives of the functions at all of these grid points, because the PDE in general relates the time derivative of the function to the various spatial derivatives. And so now you need to figure out how to calculate the spatial derivatives given these points. So you're trying to, so how do you do that? So the sort of classical way to do that is to say, well, we know about calculus. The only idea in calculus is that every function can be approximated locally by a polynomial of some degree as long as it's not discontinuous. So let's assume that it's not discontinuous. And so you say, well, let's just approximate by polynomials. So here you go. That's polynomial interpolation. This is, 5th order polynomial interpolation on these points. And then you can, if you want to compute the derivative at this point, you just compute the derivative of the of the polynomial. Now that may in fact be correct. I still haven't told you what the equation was. But if we go back to the original solution, which I told you was the actual solution, it is in fact incorrect. So the question is, how does one get around that? Okay, so now let me tell you a machine learning thing. So this is a thing which exists roughly on your phones. So if you take an image at high resolution and you downscale it, so this is a downscaled image, then what you might want to do, you downscale it because you want to save it, you want to store it with less memory. So now you want to upscale it again so that you can see it. So a reasonable way to do this is to use cubic spline interpolation between the points on the color maps. That's exactly what I just showed you with the computing the derivatives. And it sort of looks okay. So on the other hand, what machine learning has made possible is that what you do instead is you do this differently. You basically give the computer a large set of training images of faces, of images that are like this one. You let it learn the patterns from the images that you've given it, and then you basically ask it, given this coarse grid, can you please upscale it? And you can just see visually that this works much better. This is the original So we set out, basically inspired by this idea, to apply this to PDEs. So now I'm going to tell you what the equation is. So the equation is Berger's equation. So here's Berger's equation, which I showed you before. And so now what we're going to do is we're going to give a regressor or a neural network or whatever, just some regression algorithm, examples of solutions to Berger's equation. So we're going to turn the computer on. We're going to just run lots of examples. We're going to just save all the shapes. We're going to give it to the regressor, and we're going to tell the computer that given that you know the solution on these 5 points, please realize that it should be these functions are, so these are other examples of these functions, and please use that when doing your fitting. And if you do that, then it works extremely well. So this is just, I haven't told you the details, I'll tell you more in a minute, but this is just to give you the idea. The yellow curve is basically from a regression algorithm. The black curve is the right answer, and this is polynomial interpretation. And the reason is very simple. It's that if you know about Berger's equation, then you know that there are shocks, and you know that basically that this is what the solutions are going to look like. In applied math classes, we teach people to derive these things analytically, and the students jump up and down because they're so happy that they derived the analytical solution. But who gives a damn about the analytical solution? What you really care about is what are the constraints on the solutions that exist within the equation. And as long as you give the computer the examples, it can learn it even if it can't spit out and say why. So, okay, so this is the method. Perform many high-resolution simulations of small pieces of solutions. So what's nice about this is you can do this in little pieces. You can divide it into little tiny pieces and use your computer power for this, then train a regression algorithm to machine learn the manifold of the solution, and then use this to estimate spatial derivatives and integrate. So that's the method. So, okay, so it's more abstractly, given a PDE, so here's a PDE, you could sort of, as I've said before, classically, you would approximate the nth derivative as some, you choose some number of mesh points, and you would approximate it as some number of, weights, alpha k, over those mesh points. So for example, this is the second derivative operator that I told you before. So what we're going to do instead is to learn these alphas. So this is the content. To the extent that there's content in this part of the talk, I think Yohai would agree with this. This is it. So what we're going to do is we're still going to write a formula for derivatives which is linear, but we're going to, instead of deriving these alphas from calculus, how many in the room have suffered through deriving these alphas in a calculus class? I'm just curious. Only some. So I mean, remember what you do. What you're supposed to do is you're supposed to make sure they're consistent. You do Taylor series expansions and you make sure they're consistent. You might recall, if you've gone through that exercise, there are actually lots of possible alphas that you could choose. There are lots of formulas. There are books filled with them. So the point is, what we're going to do is tell the computer to please choose one, which is actually going to depend on the fields at that value of the mesh point, which then means that the way that one calculates derivatives is going to change from point to point. So for example, this is a solution of Berger's equation. The dashed line is an actual solution. The solid line is the discretization. And these are the stencils for computing the first derivative that the computer learns. And notice it has a very different stencil. So these are the weights. These are the alphas. So and so you can see it's computing a difference because there's a positive one and a negative one. And this is, but the weights change dramatically. That is, as you go from point to point on the solution. And the other thing about this is sort of heretical in the sense that normally one teaches people to invent numerical methods that work for all equations. This is a numerical method that only works for this equation. So every time you have a new equation, you have to derive a new numerical method. But see, the thing is, you would say, why would I ever do that? But suppose you care about that equation. The truth is, there are only a couple equations we care about. I mean, in truth. So what you do is you just spend all your compute on that. You store them. I mean, I don't know who you is, but somebody. And then you can compute with them. That's the idea. OK, so here's how it works. So to compute the function at a new time, you compute the spatial derivatives using this formula. We compute the spatial derivatives by feeding in the function values on the stencil into a neural network. So this is just a convolutional neural network with a couple of layers, and there are certain accuracy constraints that are put on the end. These are just details. It outputs the coefficients. From the coefficients, you can compute the spatial derivatives. From those, you can compute the fluxes. From those, you can compute the time derivatives. You then simply advance the solution in the same way as before and iterate. That's the algorithm. So actually, in the training step, to train this neural network, what you do is you basically adjust. You have to put in a loss. So you have to basically train the thing by demanding that something is true, that these coefficients demand that something is true. And what we found is the best thing this is purely heuristic, is to demand that the time derivative formula is accurate, that these coefficients are chosen so that the time derivative formula is accurate. And that's basically the law. So this is now an algorithm. Okay, so we did this. So I'm going to now show you. So this is a solution of Berger's equation. This is upscaled 32 times from the high resolution solution. The high resolution solution is the blue curve. This is Berger's equation, which is being randomly forced. And what you see is that the orange dots are what would happen with a normal numerical method if you actually just solve this using the traditional method of lines. The green dots are this method, which you see, it's not getting it perfectly everywhere, but it's tracking the solution quite well. So this is 32x upscaling. So this is 64x upscaling. So by this point, the classical one is just off the page. And you'll see this method basically stays with it. It stays with it because every time step, it's trying to guess where the shocks are. Okay, so this is a somewhat more busy version of the plot. So this is this is a solution at 8x. This is the baseline solution. This is using the classical numerical method. This is using the neural net. These are space-time plots. So space is this way and time is this way. So the solution is evolving this way. And what you see is that the neural net keeps it, even when you're at a place where there's basically nothing left, it's still producing a reasonable average of what the baseline is. So if you quantify this by plotting, for example, the mean absolute error as a function of the resample factor. So the resample factor is how much you've resampled the mesh points over baseline. So this is a first order method. This is a fourth order method. You'll notice the fourth order method beats the first order method, but that's only true when the mesh is, that's true theoretically when the mesh spacing goes to 0. As the mesh spacing gets large, that's no longer true because the mesh points are so far apart that there's all this stuff happening in between, so you can't fit the solution by fourth order polynomials anymore. The neural network still doesn't care, and it's still basically keeping the error low until basically you get up to having only a couple of 128 resample factor on this is only having a couple grid points in the entire box, at which point you really don't have enough degrees of freedom to resolve anymore. So for whatever it's worth, in case there are any experts in the room, there is, for shock-like problems, there's a state-of-the-art numerical method which is called WeKnow, which basically works by changing the discretization formula at every point in space, but it does it according to a predetermined rule that's based on the curvature of the solution, and it's sort of the neural network also beats WeKnow, which is the current state of the art. So okay, so this is Berger's equation. So the one other thing to say, and I was just checking the time. Why does the error go down?
Yeah, when you go from resample factor 2, 4, it goes down.
I have no idea. I don't know, but you know, at least it doesn't go up this fast. So an interesting question is, what does it learn? And actually, so here's a sort of interesting plot. This is a bit busy, and I apologize, but this is, for those of you who've grown up on numerical analysis, at least for me, this is sort of heartwarming. So I told you already that the stencil changes as a function of where you are on the solution. So one thing that you can do is you can compute the center of mass of the stencil. So the stencils, of course, have positive and negative, the coefficients have positive and negative signs, but take the absolute value of them and then compute the center of mass of that. That's sort of telling you where the discretization believes the derivative is localized. And if you do that, then this is a plot of the center of mass as a function of position. And what you will see is that the center of mass of the stencil is positive when the velocity is negative, and it's negative when the velocity is positive. So there's a principle in numerical analysis which is called upwinding. How many of you have heard of upwinding? We need to teach more classes. There should be more classes. This is like, anyway. So upwinding basically says that information propagates. Upwinding is essentially the rule that says that, you know, if the velocity is positive, then it's best not to, when computing the derivative, to use the grid point that's in front of where you are, to only use the ones behind you. That's basically what it is, essentially information propagation. And it's been known to work since the 40s or something. And anyway, this is in there. The computer learns about upwinding, which is sort of heartwarming. And this sort of shows statistically that the computer learns about upwinding. So we've tried this on other 1D equations. I don't know if you care. Kuramoto-Shifushinsky is a classic 1D equation for a chaotic PDE. This is the baseline. This is the neural network. These are, of course, totally different coefficients, but you'll see the neural network. By this point, the baseline blows up, and the neural network is still going. And we've also done it on the KdV equation, which is another famous equation. And essentially, in every case, this is a plot of basically so the neural network is the orange curve, sorry, and the baseline is the blue curve. And this is a measure of the mean valid simulation time. It's basically just how long can you integrate until the thing goes, no longer is reasonable. And the neural network outperforms all of them. So okay, so finally, so there are different ways you can criticize this, and I'm happy if anyone would like to start criticizing, then that would be great. But just to say, one obvious criticism is that these are stupid problems. These are 1D problems. This is the toy that you do before you actually start to do this for real. So the way to do this for real is to do this on 3D problems. That is the place where this actually has actual potential, which is as yet undemonstrated, is on 3D problems. Because that's where I told you all the computer power is going. So we're sort of starting to work on 2D problems, and I just want to show you early work. This is by Dima Koshov, who is an intern at Google, and Zhao Wei, who's a student in atmospheric chemistry here at Harvard, and with all of the other people that I mentioned before. And this is based on a problem that I got interested because of Daniel Jacob, who's not here, but who is an atmospheric chemist over there. And he basically was telling me this great story that there are pollution plumes in China that go across the Pacific Ocean, but in the atmospheric chemistry models, they dissipate before they get to California, but in reality, they don't. And the question was why? And the answer is because essentially it's extremely hard at the grid resolutions that exist to basically get solutions of advection diffusion equations that don't dissipate away. And so we've been sort of working on trying to make that work with this method. So the way that this works is I'm going to just show you one simulation, and then I'm going to stop and go to the next topic because I'm whatever. But so what Dima in this case did was to generate lots of random velocity fields, to generate an entire ensemble of random velocity fields, and then to ask if one could find a numerical method for this equation which worked for any velocity field that was chosen from that ensemble. That's a reasonable thing to do because, in fact, if you know about the physics of advection and diffusion, what you do is you put a blob in the thing and then you stretch it out. And when you stretch it out, then the only thing that matters is the shear rate of the stretching and the diffusion constant. Those are the only things that matter. So if you choose a velocity field ensemble where the shear rate is essentially in some distribution, then it should basically be able to learn the pattern. And so then what you do, the way you test this is you choose a new velocity field, you put a bunch of blobs in them, and you see how they advect. And this is a comparison between the real solution. The low resolution solution dissipates it away, and whereas the neural network basically keeps the structure of the real solution. And I want to say there's more work that needs to be done here to do whatever, but this is really quite promising. And actually, I had this plot, which I think I'm going to skip, and I'm going to summarize this and then move on to the next topic, because when do I finish? I have 15 minutes? Oh, okay, good. So I have 2 more topics, so I should end this one. So anyway, just to summarize, so the solutions of PDEs sweep out a low-dimensional manifold. This is an uncontroversial fact, which has been well known for a long time. On the other hand, to the best that I can tell, it's been practically useless. Up until this sort of machine learning revolution, which basically has really given the opportunity to learn the manifold and thus create equation-specific methods. So this type of method gives you a different trade-off than classical methods. Here you have to spend a lot of time pre-computing. Like I didn't talk about this, and what I said is we train these things on 1D problems, but when you get up to serious 2 and 3D problems at high Reynolds number or whatever, then you're going to have to invest serious computing in doing this. But once you've done it and you've trained it, then you can use it thenceforth on a lower resolution grid, and so there's a huge potential payoff. So this, to the extent that we know right now, it outperforms state-of-the-art methods. There are issues, I should say, with that statement. So one issue, just to throw it out there, which you might worry about, is that if at every time step you have to compute the stencil at every point along the grid, using a neural network. Well, neural networks are not cheap to evaluate, so now you're spending a lot of compute on that. There are ways around this that we are exploring. Probably the best way is to get rid of the neural network and to replace it with piecewise linear models, but that's for another day. And then there are lots of other issues to think about. Okay, that's that part of the talk. Now I'm going to go on to the next part of the talk. I told you this would be frenetic. But I mean, you wanted Tim to start phonetically. Okay. So that's okay. What? Yeah, exactly. Just to wake you up, because it's terrible out there. Okay, so now I'm going to move to the second topic where Ellen in the back will hopefully save me if I mess this up. So I'm going to start with philosophical nonsense, which you should criticize. So normally, the way that imaging normally works is that you have some instrument and then you take a picture of something and then your brain interprets what it is. I mean, the reason you take images is you want to characterize something or measure something, so that's normally what you do. And I mean, so in machine learning worlds, cats are very popular these days, and so you could, take pictures of cats and then you could identify them and say, oh, look, I just identified cats. And you all know that computers are very good, it turns out, at identifying cats. I mean, if they're upside down cat, you can still see that it's a cat. That's really the challenge. But at the end, you're just taking a picture of representing a three-dimensional object, and then you're interpreting the outcome. So a slightly more non-trivial example, actually a much more non-trivial example, is the example of X-ray crystallography, where one goes from a crystal to a diffraction pattern, and then one has to go through this amazing step of figuring out, what is the object whose Fourier transform is an X, right? That, it turns out, as you all know, was one of the great calculations of the 20th century. I think that's fair. What is the Fourier transform of a helix, which turns out to be an X, but of course, if you're just given the X, you have to invert it and figure out what it is, and that's a classical applied mathematics problem. That's why universities have people like me. Not because we know how to do it, but just because somebody has to explain that it's a problem. Anyway, so just to remind you of a bit of history, so the talk contains history. So this is one of the great papers of the 20th century, which is not widely acknowledged as such. So this is a paper by Crick. It was published in 1953. That's before the discovery of the structure of the double helix. And the paper was called The Fourier Transform of a Coiled Coil. So Crick, in this paper, worked this out, and then he had these formulas, these Bessel functions, whatever, and he was proud of them, and by staring at that, he basically concluded that the Fourier transform of a helix was an X, which is the first step in what happened next, with Rosalind Franklin's X-ray and everything else. So I guess I would like to say that one thing that I found, and maybe this is just aging, is that, students are very interested in analytical solutions. Everyone is like, oh, can I get an analytical solution? And their eyes light up. So if the analytical solution looks like this, you might as well use machine learning. I mean, who gives a damn, really? I mean, the only reason that this is analytical is because your computer has Bessel functions of order p in them. Actually, it used to be that they were tables in the back of a book. Some of you have the tables in the back of the book. You look it up in the table. The only reason the computer has Bessel functions of order p is because someone wrote a Python code that basically computes it for you, which is the same as, so, I think we have to, anyway. Okay, so computers can be trained to recognize cats. So this is this is Inception v3. This is one of the neural networks which is extremely good at recognizing cats. So okay, so that's all background. So now, in principle, once you know you can machine learn the answer, then you are relieved of the shackles of having to compute the inverse problem yourself, at least to a large extent. I find this a fascinating observation, right? Imaging systems in general were invented to, with that in mind. I mean, it doesn't make any sense to image something if you can't figure out, you see what I mean? So, okay, but there's a catch, and it's a big catch. So the catch is that if you want to use neural networks to tell you what you're seeing, you need a large enough training set to be able to do the classification. So you need something to do the training on. And this is very difficult to get from experiment alone, because if you're trying to design an imaging system to discover something new, then clearly you can't use that to do the labeling for you. Oh, you guys have signs. The other speakers, you should know, these guys are great. They have signs that say 10 minutes. So there's nothing, So you can't use, so you have to find some way of making a labeled training set that basically is not, is not from the experiment. And so this is why where PDEs come in. So there are systems where we actually know the equations well enough that we believe we can simulate them. And in particular, optical systems can be simulated. And so the idea of this project of Ellen is that optical systems can be simulated, and so therefore what one can do is use the simulations to create a training set. Since you use simulations to create a training set, you can make as many simulations as you want, and you can label them. And then what you can do is you can build a neural network classifier to and to basically figure out what it is in the training set. And then what you do, and this is the tricky bit, is you use the output of the neural network, which is trained on the simulated thing, to interpret the experiment. And this basically replaces crick with the neural network. And I guess what I say here, and I think this is true, is that for people who are against machine learning, let's be honest, this is as boring as the neural network. I mean, you can either say neither are boring or both are boring, but you can't have the position that what crick did is more interesting than training the neural network on the training data. At least this is what I would claim, although I'm happy to. I was supposed to be provocative first. Okay, good. Okay, so here's Ellen's experiment. So the idea was to start this on the simplest possible experiment. So you may not be interested in this experiment. But I would like to say the reason you should be interested in this experiment is because it's a great way to test this idea. So this is an experiment from Vinny Manoharan's lab in which what you do is you take n colloidal particles. These are micron-sized particles, and you put them in a well, and then you observe them optically. And you set it up so that the particles all stick to each other. And so if they stick to each other, then they can, of course, stick to each other in various ways. And depending on the number of particles you put in, there are more and more ways they can stick to each other. And the question is, well, what happened? So what do you see? So the nice thing about this is these are micron-sized particles. You can image them optically. It's a simple system. There's a finite set of answers. And in fact, for some strange historical reason, Vinny and I were obsessed with this for some period of time. There was a graduate student named Natalie Arcus who figured out all of the structures that can form when these things stick to each other. And so for 3 particles, it's only a triangle, and for 4, it's a tetramer, and for 6, it turns out there are these 2 structures, and for 7, there are 5 structures, and for 8, there are 16 structures, and for 13, there are 98,529 structures. But the point is we know them all, and thus can generate training sets. Okay. So you might say so here's a bright field microscopy picture that Ellen took. And so, I mean, one thing you, of course, could do is try to interpret this in bright field. But it's really very hard if you look at this and try, especially when the number of particles gets high, to look at the ones on the list to figure out which one it is. I mean, and so it turns out that this could be either of these 2 possibilities. And just to show you the subtlety, this one has a bond here, and this one has a bond here, but these 2 don't touch. And you have to be able to distinguish these 2 if you want to say what this is. And here's a bigger object where you basically just have no shot. Okay, so it would be wonderful to do what I just said with bright field microscopy, but it's hard to simulate bright field microscopy. So something that's easier to simulate is to make a hologram. And so what Ellen does is she makes holograms. She sends incident light, she scatters it off of the cluster. That then creates 2 wavefronts, both the original incident light and the scattered wavefront. They interfere with each other, and they produce a hologram on the microscope. And now the question is, what structure does this hologram correspond to? So classically, the way that you do this is you take the raw hologram, you guess what the structure is, you then do a simulation of the hologram of the structure that you guessed. You then create some loss function, you do refinement, and you try to get it to converge. And this is quite tricky to get to converge. Okay, but the idea here is to basically take the simulations, make images whose labels you know because you know where you created them, and then get the neural network to figure out which of the structures you're observing. And so in order to do this, you have to make a training set. So of course, the way that this works, so this is the hologram of this cluster when it's this far off of the imaging plane. So the way that Ellen does this is that for every cluster, she rotates it in all possible, she rotates it randomly, and she translates it up and down and in the box so that the hologram moves around. It especially changes when you move it closer to the imaging plane. And so for each cluster, you need a very large training set to be able to do it because you're only getting one angle to call, and you need to basically have all possibilities. So here's an example of so these are holograms all for the same cluster. They look sort of different. This is a different cluster. This is a different cluster. To me, these things all look the same. This is for a different cluster. This is for a different cluster. So you see, you just simulate a lot. That just costs computer power. So Ellen made 65,000 training images for structure. So that's 250,000 total training images, and she held back 65,000 for a test set. And then basically used Inception, the same neural network that identifies cats, except that she added a couple of layers on the top. So she froze the architecture. She added a couple of layers on the top and basically fine-tuned the last couple of layers to do this problem. And after training, the neural network obtains 98.6% test accuracy. This is on the 7 particle clusters. There are 5 of them, and on these 5, it gets 98.6% accuracy, so it correctly associates the holograms to the thing. So that's fun, but that's a computer, so who cares about computers? So what we really care about is the world. This is the confusion matrix on the test set, basically, of the simulations. So this is basically showing you that where the errors are. So there's some small amount of mixing, which presumably could be eliminated with a bigger test set and more training. But anyway, so now the fun part of this is to use an experiment to test this. So what Ellen does is to take a bunch of particles, puts them in an optical trap. She lets them go, and they form a cluster. The particles are about a micron size. There's 660 nanometer light, and there's some number of pixels per micron in the camera. So she then takes the experimental images, and she puts them into the neural network. So this is a very dangerous thing to do because there's noise in the experimental images. So this is the raw hologram, and this is a simulated hologram, which is close to it, and they don't actually look the same. But anyway, what the hell? You only live once. You might as well do this. And so Ellen quite wisely starts by smoothing the hologram. Part of the and when she does this, the neural network classifies 59% of the frames, which is actually not bad considering how close these things are to each other. If you look at the top 2, that is, if you look at the top 2 scores, it classifies 90% of the frames. It's not good enough to be an imaging method yet. To be an imaging method, you need to push this number way up, but she's been doing this for a couple of months, so there's hope. And this is the confusion matrix of the one movie she shoved in. So this is the true structure. This is the number of correct ones, and it's basically confusing it with these 2. It doesn't tend to confuse it with these, which is good, but there's some confusion. But as I said, the top 2 error is 90%. This is the top 1 error. So in order to do better, basically, maybe I'll skip forward because I'm running out of time. So in order to do better, the key element that's missing is physics. Namely, what you really need is to make a noise model of the experiment and to add the noise into the data to basically correct for it. Because of course, in the same way, when you train a speech recognition model, you better put other people speaking in the background because you don't want it to contaminate you speaking. There's other crap in the experiment that's being contaminated, and that's what has to happen. So in order for this approach to work in general, clearly this is not the most exciting thing to image, but the question is whether one could really invent an imaging method going this way. You need the ability to generate a training set, so you have to be able to solve Maxwell's equations on the thing you're looking at. You need a neural network to classify, and then you need some noise classification in the experiments. So I think I'm now out of time, and so I'm going to skip the last one and just say thank you, and see you missed all these slides. Anyway, that's all.
Thank you very much, Michael. Maybe we can take one question. Yes.
So your structure has 7 components.
Wait, I didn't hear what you said.
The structure that you were showing us has 7 components.
Yeah, 7.
So let's say if you extrapolate this to like some new experiment set, you add more components to it. How much can you retrain this neural network to this?
Right. So you could. So this is a model problem. So the beauty of this model problem is that for any number of particles, at least up to 14, we actually know all of the structures that can form. So in principle, you could do what Ellen did on that problem, and to then you'd have a new neural network to train. So it's possible, of course, that you could do what you're suggesting and add the different numbers together and get some generalizability, but we just don't know. The idea I wanted to leave you with, though, was the idea that if you can simulate the imaging system, to me, this is a completely different way of using a computer, right? If you can simulate the imaging system, then in principle, you can use it, and you can simulate the noise, which is the interesting bit. Then in principle, you can use it to build something which observes things that you wouldn't ordinarily be able to interpret. I think that's the challenge. Anyway.
Okay. Well, thanks, Michael, again.